Welcome back to this NPTEL online certification course in the molecular rearrangement and reactive intermediates. So last class I started talking about the generation of carbon ion, their stability. I talk about the pK scale and about their reactivity. In the today's class my focus will be talking about several rearrangement reaction which was done using carbon ions. So I am going to talk about various different rearrangement reaction. So starting with the Neber rearrangement, Smiles rearrangement, I am going to talk about the true Smiles rearrangement, introduce you to the Claisen rearrangement and different variations. So my first rearrangement for the today's class is going to be the Neber rearrangement, which is going to be a rearrangement of O acylated ketoxime, which is going to convert to the corresponding alpha amino ketones. So you guys have familiar with this type of ketoxime. If you remember in the previous class in the carbocation, when I was talking about the Beckmann rearrangement, I was talking about this formation of the OTS, and if you remember I was talking about some sort of a fragmentation, because if you have a stable carbocation generation tendency, then instead of the Beckmann rearrangement there is a fragmentation happen. I also talk about those things. So here I am talking about something else, that if you start with this type of O acylated ketoxime starting material here and treat with so you have a potassium ethoxide in ethanol and acetic acid is going to convert to a alpha amino ketone, which can be going to convert to the corresponding OET. Okay, it will be a ketal formation going to happen in presence of you have a acetic acid already there and you have a ethanol. So it is going to form this ketal. So what is happening in the mechanism? Let's try to understand. That you have the starting material, it was treated, so it's a form after you treat with the NH2OH. So you start with the corresponding carbonyl, treat with hydroxylamine, then you try to make it as a leaving group. So you try to make this OR as a leaving group. Once you treat with base, is going to abstract this proton here, okay, and generate a carbon ion. So now this carbon ion can attack to the nitrogen and eliminate this group, this OR, going to form this 2H agerine. Once is forming this 2H agerine, now in place of proton, it is this nitrogen is getting protonated. So this nitrogen is getting protonated. Now this the water can attack here in this position, and then formation of this particular intermediate. Now in presence of acid, what is going to happen? It can even protonate again, and this will allow to open up the aziridine, which is going to form these alpha amino ketones. Okay. It can also propose that this reaction can also go through a nitrine intermediate, and after formation of the nitrine it can just go for insertion to get to this particular 2H agerine compound, which can further goes for this reaction and goes to the corresponding alpha amino ketone compounds. Okay, I hope you guys understood this rearrangement, and I am going to give you some example here. You can see first thing is in presence of hydroxylamine, and then in place of tosyl chloride and pyridine. I already told you the structure of tosyl chloride before. So it's a paratoluene sulfonyl chloride. It's going to make this NOTS. Now in place of the potassium ethoxide and ethanol, and then with the HCl, it's going to form this alpha amino ketone, which is going to form the corresponding ketal. Okay, and this actually further converted to a very important bioactive compound. So as I told about this this rearrangement, but these reactions are not stereospecific, okay, and the reaction is generally carried out in alcohol solution containing alkoxide base, which we have seen before, okay, like potassium alkoxide in ethanol. So now I am going to move to another rearrangement. It's called Smiles rearrangement. So Smiles rearrangement is a very important reaction here. What is going to happen here? It's a intramolecular aromatic nucleophilic substitution. I am sure we are, I think all of you are very familiar with aromatic nucleophilic substitution. Here what is going to happen? We are going to add one more term here, intramolecular. Okay. So if you see the first example, which was discovered in 1930, going from this starting material to the product, what changes happened? I can clearly see that this bond between this nitrobenzene and this SO2 is actually broken. And then this nitrogen of this phthalimide actually now came and forms a bond here. So you can clearly see that happening here, that this nitrogen is attacking here in this and is forming a bond with this nitrobenzene, and then this SO2 is getting out. So what is happening here in this reaction? So you have this type of XH in your reaction, which could be a amine, could be a alcohol, could be a NaCO, like like a protected one. So, different type of, heteroatom, where you have a, proton which can be easily abstracted to make a, carbon ion, some sort of anion, not a carbon ion, sorry for that, it will be anion which is going to attack, here. So, it's going to go for some sort of a ipso substitution, you can see clearly is going to attack there, and then, it can, cleave that bond through, this type of transient state, and then after that it can form this product. So, I am going to give you, more example of this reaction here. So, starting from this particular compound, which having a benzo, thiophene. So, first in the presence of sodium hydride, it is going to abstract the more acidic proton which is here. This is getting abstracted to generate a carbon ion. Now, this carbon ion is going to, take part some sort of a, Michael type addition here, because you have this alpha beta unsaturated cyano group. Now, now it is going to generate a negative charge here. So, if you try to draw this, then what is going to happen here, that there will be cyano, there will be a negative charge, and then there will be a oxygen which is attached here. There will be 1, 2, CH2, and then there is another carbon, and then there will be a cyano group. So, now what is going to happen? Now, actually this negative charge is going to come back and break this carbon oxygen bond. Okay, that is going to form this type of, O minus species here, which is now going to attack to this cyanide CN to form this species. Now, this N minus can attack to another CN here, and finally through this condensation it is going to form this, benzothiono furo, pyridine skeleton. Okay. So, what is happening, one after another, first is forming a carbon ion, stable carbon ion, then it is attacking one after another, center, one after another cyano group, and then forming this product. There is another example here. If you look into this molecule, once you treat with a base like LiHMDS, I have already introduced you about LiHMDS in the last lecture, and I talk about their pKa. So, it is a pretty strong base. So, it is going to abstract a acidic proton here. So, now it is going to abstract this proton from this NH ethyl, forming this type of, N minus species. Now, that can attack, that can go for a SNAR to, so that can, take part a nucleophilic aromatic substitution to get rid of this corresponding chlorine to form this product. Okay. Now, moving further, we are going to do Smiles rearrangement. So, it is a one type of Smiles rearrangement, but the incoming nucleophile is very strong. Okay, so that no such activation is needed in the arene ring. What does that mean? That if you seen in the previous example, we are talking about that the ring which is getting attacked will always have some sort of electron withdrawing group like nitro group. So, you need some sort of a arene activation, but here you do not need it. So, starting from this compound, once you treat with the butyl lithium, what is going to happen is going to abstract these toluene protons here to generate a carbon ion. Now, this carbon ion is attacking to this carbon here, going for a nucleophilic attack here, and then it is going to stabilize the carbon ion, followed by the cleaving of this carbon sulfur bond to generate this compound, which will take a proton to form this desired product. We can also do this reaction using this, for this substrate using sodium hydride and HMPT. So, sodium hydride is going to abstract this NH2 proton of this amide, and then this NH minus species is going to, go for. So, once it forming this, NH minus, it is going to go for another sort of a, attacking in this carbon, and then after that the cleavage of this carbon oxygen bond going to generate this corresponding product here. Okay. So, moving further, we are going to introduce you to the, Claisen rearrangement. So, Claisen rearrangement was actually, discovered at 1912, was discovered by, Brainerd Ludwig Claisen. So, this is a very powerful reaction for formation of carbon-carbon bonds, and there are different variation of this, rearrangement was developed over the years, and it is still a very important reaction. You will see for a natural product synthesis, a lot of times, this reaction was used. Now, we are going to talk about the reactant. So, what is the reactant and what is the product? So, the reactants are allyl vinyl ether or allyl aryl ether. So, what is happening here? So, this compound is a aryl group here, and then there is a allyl group here which connected through oxygen. So, this is called a aryl allyl ether, or you can have a class here where you have a vinyl group next to the oxygen and then an allyl group here. We call it allyl vinyl ether. So, once you treat this compound under heat, it is going to rearrange, because there is nothing that there is no change in the molecular weight. Only thing there is a rearrangement happen where this allyl group which was with the oxygen at the beginning now moved to the carbon. So, it is moving from this oxygen to the carbon. So, now because of this carbon oxygen bond is getting cleaved, it is forming a phenol. In case of vinyl and allyl ether, what is happening here? In this reaction, there is a carbon oxygen bond formation happening. So, it is a carbon oxygen double bond formation happening, and there is a double bond happening formation. So, what is happening in this reaction? That there is a cleavage of this carbon oxygen single bond. At the same time, there will be a formation of carbon carbon bond and carbon oxygen double bond. And so, this type of compound is actually, so if you talk about alpha, beta, then this is a gamma and then delta. So, it is a gamma delta unsaturated carbonyl compounds which can be formed by Claisen rearrangement. We are going to try to understand the thermodynamic driving force this reaction. As I mentioned, that you are forming a carbon oxygen pi bond, and at the same time you are forming a carbon carbon sigma bond. So, that is the driving force here. Of course, this reaction is exothermic, and this reaction actually goes via intramolecular fashion, and actually it goes via some sort of a cyclic tangent state, which I am going to come in a minute. So, here actually, as I said, there is neat change will be 0 sigma and 0 pi bond. So, that means you are seeing here that there is a pi bond which is also getting broken, and there is a new bond getting formed. At the same time, there is a carbon carbon bond and carbon oxygen double bond is forming. I told you that this reaction is exothermic, and the reaction rate or the exothermicity will be increased if you can able to bring a substitution in this position which can push electron density. So, if the X will be a group of nitrogen, oxygen, or some sort of a group which can push electron density, that is going to make this reaction even faster. So, we are going to talk about several variation of this type of reaction where we change this X to oxygen and nitrogen. As I told in the last slide, I am going to talk about the transient state. The reaction goes by a chair-like transient state. Also, we can explain this reaction through a boat-like transient state. And here you can see there will be a formation of this carbon oxygen in double bond. There will be breakage of this sigma bond here, and then there will be formation of sigma bond here. Okay. So, now we are trying to explain this reaction through the Hofmann rule. So, if you try to look into this orbital here which is forming the bonds here, we can see these bonds are forming through a suprafacial manner. So, there is 3 different suprafacial bond formation happening here. So, and they are all 2 pi systems. So, we can see the 4q plus 2s will be 3. There are no 4qr system, as there is no 4 pi system here. So, total will be 3, which is a odd number. That is that means this reaction is thermally allowed. This can also explain through the boat-like tangent state as well. So, now we are going to talk about different type of variation of this Claisen rearrangement. So, the first question arises that in the Claisen rearrangement, what is happening, that if we start with this 2 terminal. So, if we have this 2 methyl group in the 2 terminal position, now the question comes, what type of substitution they have. Suppose we are talking about a Claisen rearrangement here. Now we are talking about if both are trans, means this is a trans, this is a trans, or they are both are Z or E. So, if it is E, or so if it is a EE like this, or if it is ZZ, what will be happen, and what will be the major product in this Claisen rearrangement. So, what is happening, what we find out, if it is a ZZ or EE, in both the cases the anti-product, means both the methyl will be anti-position, will be the major product, and the C will be the minor product. So, then we are trying to understand this from this type of transient state, what is happening here. In the transient state, if you see that in particular this transient state where both are actually Z, you can clearly see that this is a methyl which is a Z, and this is a E configuration. Now, you can see once they are forming bonds, this methyl is up and this is down. So, this is forming the anti-product as a major product. In case of once both are E, in the junction what is happening, you can, so now I have drawn them, both the methyl group here. So, this is a methyl, this is a methyl, so they have only a Gauss-Butane interactions, and once they are forming the bonds, again the one of the methyl is up, one is down, is giving to the corresponding anti-product as a major product. Okay. In the both cases, you can see in the first cases they have actually have a both the methyl in the anti position, here they have a Gauss-Butane interactions. Okay. So I can introduce you to the enantioselective Claisen rearrangement. So if this reaction need to be asymmetric, it was done that in presence of some sort of a boron based Lewis acid using a chiral backbone. So for this particular compound, once it is reacting with this particular boron compound, it is actually forming some sort of a chelation complex. So these both of these oxygen actually attacking on the boron, forming this type of some sort of a boronate complex. Now what is happening, as this boron is bind with this phenyl ring, it is actually blocking one of the face of the phenyl ring. So now what is happening, this Claisen rearrangement happening only one of the particular face of this phenyl ring. So it is happening to the top face, giving to this particular product with 95% EE. Some more example about the Claisen rearrangement. So starting from the limonene, this compound can be synthesized easily. After that, the reduction of this aldehyde group, and then followed by synthesis of this type of vinyl and then allyl ether. Then once this compound was heated in 200 degrees Celsius, it can go for a 3,3 Claisen rearrangement to get to this particular compound. You can clearly see this Claisen rearrangement happening, and it is actually coming up instead of down, because to avoid some sort of a steric interaction with this type of isopropyl group. So this compound can further able to convert to the corresponding natural product after some successive transformations. So there are different variation of Claisen reagent. I am going to explain each of these variation to you. I am going to talk about the aromatic Claisens. I am going to talk about the Ireland Claisens, Johnson Claisen, Essen-Moser Claisens. So let's start with the aromatic Claisen rearrangement. As I mentioned in the introduction to the Claisen rearrangement, that this type of aromatic Claisen rearrangement was the one which was done at the beginning. So it was the one which was discovered at the beginning. So it actually goes through this type of 3,3 sigma-atomic shift. You can assign this 1, 2, 3 at the same time 1, 2, 3. It goes through this type of intermediate where you can see there will be a proton abstraction going to be, which is going to finally going to get to the corresponding phenols. Okay, so I think the mechanism is given here clearly. Now the question comes that if your ortho position is blocked with two groups, now what is going to happen? Now instead of happening 3,3 sigma-atomic shift, now it will going to go for a 3,5 sigma-atomic shift. Proton abstraction from here, it is going to get to the corresponding phenol. Again, this things was given here. They starting from this allyl phenol ether. You can see this because this is attached with the phenol ring. We can see this allyl phenol ether goes to this dienone first, and then it goes to the corresponding product. Okay. So now I am going to talk about, I think, the first variation of this Claisen rearrangement, which is the Ireland Claisen rearrangement. So this is another important Claisen rearrangement reactions. So this actually goes via formation of the silyl stabilized enolate derivative. So this is the one going to form, and then what is going to, so this is the important thing, that it goes via formation of this silyl stabilized enolate derivative. So starting from this ester, what is happening first, so this proton is getting abstracted by using the stronger base LDA to form this type of silyl stabilized enolates after it react with the TMS chloride. Then it is participating in 3,3 sigma-atomic shift. Now also you can give 1, 2, 3, 1, 2, 3. It is going for 3,3 sigma-atomic shift. Now it is forming alpha, beta, gamma and delta. So it is forming the gamma delta unsaturated carboxylic acid instead of the ketone which is forming in the Claisen. So this is the mechanism which I was showing in the previous slide, that it is going to abstract this proton to form this carbanion, which is going to form this corresponding lithium, which is going to trap with TMS to form this corresponding silyl enol ether, which is going to participate in the Claisen rearrangement in presence of heat to get to this corresponding carboxylic acids. Okay, which has a gamma delta unsaturation. Here is one important example here. So what is happening, that in this particular compound, I think I have explained you during the Claisen rearrangement, that if you have 2-methyl here, now you have a very similar scenario. In presence of LDA, in presence of THF, using the corresponding silyl chloride, it is forming the E enolate, and that E enolate is participating in Claisen rearrangement to form the syn product. But once you treat with LDA with HMPA, so once the HMP was added, then it is forming Z enolate instead of E, and now it is actually forming a anti-product instead of the syn. So now we try to understand the the tangent state of the syn product first. Let's try to understand for this one. So from E enolate, if you try to draw the corresponding tangent, you can clearly see. So this methyl and this methyl actually both are down, which is going to end up making the syn product, and they have only a Gauss-Butane interaction is present there. Very similarly, if they are Z enolate, then you can see that this methyl is actually down, but this methyl is up, and they have a Gauss-Butane interactions, and from this tangent state they can able to form to the anti-product. Now we will try to understand that why first of all it is forming a E enolate in presence of LDA THF, and why it is forming a Z enolate once you put HMPA. So in general, once this enolate formation is happening, if you try to draw a tangent state for that using this LDA, which have this 2 isopropyl group here with attached with the nitrogen. Now you can see in this particular tangent state, when this methyl is in the axial position, you can draw this maybe in the better shape to keep this methyl in the axial, then there will be a 1,3 diaxial interaction between this isopropyl and methyl. So it will always prefer this putting this methyl here, okay, keeping this hydrogen up. So what is happening in that case, from this particular tangent state, it is going to generate the corresponding E silyl ketene acetal. So it is going to generate the corresponding E enolate, and then it is going to generate the E silyl ketene acetal. But the question comes, once you add HMPA, what is happening? Once you add HMPA, now the HMPA actually binding with the lithium, which I have shown here. Now once the HMPA is binding with the lithium, now this is actually a bulky group. Now what is happening? It is not going to prefer for these particular conformations where you have a methyl, because now if you can imagine that you have a HMPA here, which is a bigger group, and you have a methyl here, then they can going to get interact. Okay, so stop that. It is going to prefer for this particular tangent state, at least to avoid this type of it still prefers to put methyl in this position, axial position, not in the other position, because to avoid this type of interactions. So that's why in case of HMPA, the Z silyl ketene acetal will be measured. Now there is another example when people used zinc chloride for this reaction to make some sort of a chelated complex. So starting from here, first thing in place of base, it is going to abstract this proton, then it is going to make corresponding, so it is going to make corresponding enol. Now this enol is getting stabilized with the nitrogen and this oxygen, it is the zinc going to form a complex to stabilize this corresponding tangent state, which is going to take part in the Ireland-Claisen rearrangement to get to the corresponding gamma delta carboxylic acid, gamma delta unsaturated carboxylic acid. There is another reaction for this Ireland-Claisen rearrangement. In this particular reaction, what is happening in place of LiHMDS, which is a base which is abstracting this proton to form this carbon ion. Now that carbon ion can go for enolization, and then it is now going to trap with the TMS chloride to form this corresponding TMS, OTMS, and then once you have this one ready, it is actually ready for this 3,3 sigma atomic shift. You can now clearly see this 1, 2, 3 and then 1, 2, 3, which is going to form after the 3,3 sigma atomic shift. It is going to form this corresponding product, which is going to convert to the natural product. There are more example here we can bring. So here again using, I think there is a error here, it will be LDA, not LDA. So in place of LDA, what is happening? It is abstracting this proton, forming a carbon ion, then it is forming the corresponding enol. Now once it forming corresponding enol, now it is going to trap with corresponding it can react in this way also, that once it is forming the enol, it can also go for this 3,3 sigma atomic shift to get to this corresponding you can see now also it is this alpha, beta, gamma and delta. So it is the gamma delta unsaturated carboxyl is going to form. After using several different reagents, it is going to convert to the corresponding natural product. Starting from this, it is going to, after several transformations, it can convert to the corresponding natural products. There is another example here. I think this is a very interesting example here. First, using this base like DBU can able to abstract this proton here to form this corresponding carbon ion. Now this carbon ion can form corresponding enol, which can be trapped with corresponding TMS chloride to form this corresponding OTMS. And now if you see, it is already ready for your 3,3 sigma atomic shift, because it is 1, 2, 3 and 1, 2, 3. Goes through this type of tangent state to get to this corresponding product, and from there it can able to convert to a natural product. It can also, once you use LDA with HMPA, now again we have learned with that with LDA HMPA it is going to again abstract a proton from here. So now you can see there will be a proton abstraction from here, is going to form this O minus is going to trap with your TMS chloride, then it is going to go for a 3,3 sigma atomic shift to make this corresponding compound. So now once you have this OTMS here, so it will form a double bond and a OTMS, and then it is going to perform this 3,3 sigma atomic shift to form this compound, which will be further converted to this corresponding natural products. So there is another example of Ireland-Clayton reaction. So here what we are seeing that if you have a particular stereochemistry, what is going to happen in the product. So suppose starting from this particular compound, what is happening? First thing is the the deprotonation of either of this proton from here, one of this proton, formation of carbon ion. Then after the formation of carbon ion, you are using, now what is happening? You are using the TBS chloride. So once you form this double bond here, and here you will be OTBS. Now it is going to be ready for the corresponding 3,3 sigma atomic shift. And once you are going to take part in the 3,3 sigma atomic shift, we have shown the corresponding tangent state here, and then from this tangent state through 3 sigma atomic shift, it is going to form this corresponding product here, because you have, and it is going to convert to corresponding ester here, because we have used this TMS diazomethane here, which is going to convert this corresponding acid to corresponding ester in the product. From there it can able to convert to this particular natural products. Okay. So here what you have seen here, we started with this particular stereochemistry of this allylic alcohol, and you can see in the product also after this 3,3 sigma atomic shift, the stereochemistry actually remain intact here. Okay. In this part of this course, what you have learned, we have learned about different type of rearrangement using carbon ion. We have learned about the Nemer rearrangement. If you remember, we talk about the Smiles rearrangement as well, and then two Smiles rearrangement where you have a stronger base and you have a unstabilized carbon ion which can go for the two Smiles rearrangement. Then I talk about Clayton rearrangement. I talk about the tangent state of the Clayton rearrangement. I talk about the different variation of the Clayton rearrangement. I have introduced you to the Ireland-Clayton rearrangement, and we talk about different example. And in the next segment, I am going to introduce to the other Clayton rearrangement, which is the Johnson-Clayton rearrangement and the Eisenhower-Clayton rearrangement. And you should go through this textbooks, which is the Stuart Warren, which is very good textbook for this with Clayton and Stuart Warren, and then you can go through this another textbook for the Carey Sandberg. And of course, I think these books should be a very good books for going through all the different topic I am covering in the class. And thank you all for listening, and I am going to see you in the next class. Thank you.